Okay, so we're going to talk about rates of change. Um, and then we'll get into instantaneous rates of change. We'll talk about slopes of secant and tangent lines. Just so you know, section 2.4 is the last section of chapter 2. It ties very closely to limits. And then it's 3.1. It's kind of very close to 2.4. It starts talking about the derivative. And then we really get into theory in 3.2. Then we get into techniques in 3.3 and so forth. So, I guess we used your mom. Sorry, we used to use Mr. Dioli for this one or someone else, but anyhow. So Mrs. Perone persuades Mr. Dioli to get a Twitter account. By the way, SHP, second happiest place on earth. You guys see that connection there? So it's a really good marketing tactic that Mr. Dioli does. I didn't get it until like my 10th year at the school. So when he calls this like the second happiest place on earth, he's actually trying to tie it to SHP. So after Disneyland, we're the second happiest place. So now you get it good. It took me forever to get it. So anyway, second most happy place on earth. Ends up with 30 followers after 3 hours and 100 after 5 hours. Okay. So fine. Mr. Dooley creates this account, whatever, right? And after 3 hours, he gets 30 followers. At 5 hours, he gets 100 followers, right? So you want to know, was it change in the number of followers in the time period from 0 to 3? Okay. Well, obviously he gained 30 followers, right? So that's pretty straightforward, right? He initially had no followers. Now he has 30 followers, right? So that's what we're asking, just to change the number of followers. It's 30, right? And then how many followers does he gain from hours 3 to 5? 70. So would you agree there's a more rapid increase in that second interval compared to the first interval, right? And that's what calculus is about. It's about looking at rates of change, at least differential calculus, the first part of calculus. Um, Another good example would be when we talk about COVID, right? We lived through that 6 years, 6 years ago around this time, right? There was COVID. You guys were in fourth grade. I've actually felt so bad for you guys, the fourth and fifth grades, because to do Zoom schools must have been really hard. It was hard for high school too, but as you guys remember from COVID, people talk about the flattening of the curve or how like the curve like was spiking. I sometimes kind of joke that maybe COVID was so bad because people didn't know calculus. Well, because if you think about it, if you look at the curve, a lot of it, when you see it increase more steeply, that's a derivative, right? If you think about the derivative is definitely going to be much higher or much more steep when people are getting more infected, right? As time passed. So we want to look at rates, and this could be applied to so many things. It could be applied to money, right? That's a great example. You could apply it to population growth. So there's a lot of cool applications that come with derivatives. But anyhow, let's get back to this problem on Ms. Dewey's Twitter account. So during which two time periods we expect the rate to be the fastest and why? So I expect this one, right? And why? Because what I'm going to do is I'm going to do my average rate of change. I'm going to call this an average rate of change. You'll understand why it's called that in a moment. The average rate of change is very simple. It's going to be the new minus the old divided by the time interval or the time elapsed. Let me rephrase that. So from 0 to 3, what was the number of followers at 3 hours? What was the number of followers at 0 hours? And what was the time elapsed? 3. So 30 over 3. So on average, that's why it's called an average, he's gained 10 followers per hour on average. Now, if you think about it, what is that going to be geometrically on the graph? What does that represent?
Linear.
It's a linear function, and it's going to be connected what 2 points?
The initial and the final.
0, 0, and 330. And what about this line? What property of this line would be the same value as this? Slope. There we go. Just everything we do this month is all about slope. Slope, 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 slope. It's all about slope. So yeah, the slope is 10 on average, right? So for example, what if you're driving from here to Los Angeles? It's about 4 miles to say, and you're driving kind of fast. Let's say you get there in 5 hours. That's pretty fast to get from here to LA in 5 hours. Pretty darn fast, right? What would be your average speed if it's 400 miles from here to LA and it took you 5 hours to get there? 80. Now, are you going 80 the whole time though? No. There are times when you get on like Highway 5 when there's the open road and you don't see a cop and you maybe have a nice car, you want to gun it, you might go 100 miles an hour. Be careful if you do that and you have good tires, but you could do that. Or you hit traffic when you get to LA and there's a little bit of traffic or you're trying to get out of the Bay Area, maybe you're going 40 miles an hour or something like that, right? But it's just an average. Now, instantaneous rate of change, we'll talk about that later. That's another thing, like at a particular moment. But average rate of change is what we care about. Now, what's the average rate of change for the second interval from 3 to 5? 100 minus 30 over what? So it's 70 over 2, which is 35. So we see a spike, right? Kind of like a COVID. Like as more and more people got infected, you start seeing a sharper rise in the curve, right? And that's why people are talking about, we're so adamant about we need to see a flattening of the curve because we need fewer people to be getting COVID after that. So anyhow, and so if you draw that slope, kind of looks like that. Definitely a steeper line, right? That blue line. Now, when you connect 2 points on a curve, do you guys know what kind of line that's called? Does anyone remember the term for that from geometry, from his Xerox class? I won't tell if you don't know. Or the sophomores who probably had geometry in middle school. It's called a secant line. What if? And actually, I didn't expect you guys to know that because that's kind of a. So these are secant lines. These are called secant lines. So secant line is when you cross 2 points. Now, what if you just graze the graph at one point? Does anyone know what that's called?
Tangent.
Good, tangent line. Good. The secant line crosses 2 points in a curve. So both the pink and blue lines are secant lines. But if you just graze it, that's called a tangent line. We'll talk about that when we talk about derivatives. The slope of the tangent line is the derivative, and that's actually the title of this section about tangent lines. So we're going to get there in a moment. Um, okay, cool. So what we just did was we talked about the average rate of change, right? In other words, you consider the increase decrease in number of followers with respect to the amount of time elapsed. So find the average rate of change. Actually, I already did it. So number four, we already did actually. I should know these notes better. My bad. Um, so we already did number four. So we're good. So again, that was 10. That was 35. And although average rates of change are sometimes measured per hour, like we did from here to Los Angeles, right? We talked about that. Or something you do it per minute. I'm not sure why you'd want to do per minute, but you could. Actually, for those who drive, so you have your speedometer, right? You also have like another thing that tells you the RPMs. And sometimes your car might be going 6,000, 7,000 RPMs, right? What does RPM stand for? Revolutions per minute, right? For those who are taking physics, you might maybe you guys have done, I don't know. But revolutions. So if you think about a car engine, right? There's pistons and they're going up and down really fast, right? If you have an electric car, it's different, but just think about more old school cars. It's kind of the same thing. Like usually we tend to look at things per unit time. Doesn't have to be that way for rates of change. Doesn't have to be at all. Could be, you know, something how something's changing per something else. So you don't always have to use or the other great one, miles per gallon. That's a rate, right? How many miles per gallon do you get for your car? Electric cars obviously have great miles per gallon, right? Well, actually, hybrid cars, let me take it back because they don't take gas if you're electric, so I take that back. Um, okay, so average rate of change. So mathematically speaking, here's all it ever is. It's essentially delta y over delta x, or f of b minus f of a over b minus a. That's all it ever is. Sometimes we use delta f, so delta y, f and y, they're interchangeable, right? So x cube, you guys know what's going on there. What are the points in x cube? Oh, geez, I need to adjust this. Sorry about that. Here we go. Okay, what are the points on x cube? Like 0, 0, what else? Yeah, 2, 8. Yeah, definitely want to go up to 2 because they said so. Okay, and if I draw a curve, sorry, a line that connects those two, it's gonna be incredibly steep. Okay, so that green line, I want the slope of that green line. So the average rate of change is the slope of the green line, which we call a secant. Let's call it a secant line. Pretty simple, right? It's just going to be f of 2 minus f of negative 2 over 2 minus negative 2. What's f of 2? And f of negative 2 in the bottom. So 16 over 4, you get 4. So the slope of the green line is 4. And actually, I did a pretty good job drawing it. Look at that. Up 4 over 1, up 4 over 1, down 4 over 1. And I'm trying to keep my ego in check. Down 4 over 1. That's a pretty good line, right? That looks pretty good. So what do you notice? What does it remind you of? Well, I just already answered that question over here. I already answered it. It's just going to be the slope of the green line or the secant line. So visually, this average rate change is called the slope of the secant line. So this should all be this should be like algebra 1 type stuff right now. Like very, very basic, right? You'll see how limits will come into play in a moment. Um, okay, questions so far? Good. All right. Let's keep going. Yeah, so recall from geometry, um, that's a tangent, and that's a secant. Where a tangent touches just one point. It's one point. Secant touches 2 points. Okay. Let's do this one. How would you work this out? Yeah, I had a little fun with this one here. You guys see how I set it up first, right? Does that make sense? 1.4, right? Take difference of the outputs and then divide by the difference of the inputs. How did I simplify that?
But it's still done here.
What was I start?
You divided 12 by 5.
Yeah, so I use a log property. You guys do need to remember that. So we'll review that if we have to. I have a worksheet in case you guys forget. But whenever you have two logs of the same base and there's a minus in between, you can treat it as a quotient. What if I had a plus in between? What would I do? Multiply, good. What if I had natural log of 12 times natural log of 4? Is there a shortcut there? The times and a minus? No, there's no shortcut, right? Or if it's a divide, there's no shortcut, right? It's only when there's a plus or minus in between you can treat it. What if that number being multiplied? The left of one of the logs. What happens there? You guys remember? Yeah, if it was like it's like a 3 there, I can roll it back and makes it 12 cubed, right? You can do that. So I love my answer like that. You could, if you wanted to give an approximation, you could. But again, I'm trying to teach class like an AP class now. And the AP tends for exact answers. That's an exact answer. Usually, most likely, what would happen, a question like this, which maybe you could see as an AP style question, multiple choice question, they could ask that and they'd probably present the answer like this, right? This could be non-calc because obviously you can't do natural log in your head, right? That's too hard to do. So you just want to be mindful of exact answers and condensing things. All right, we good there?
Wait, on the AP Calculus exam, is there going to be like a non-calc?
Yeah. So what they do, they start you off with 30 multiple choice non-calc questions. This is true for both A, B, and BC.
But you can't use any calculator?
Nope, no calculator. And then the second that's you get I think an hour to do that. You get an hour to do 30 multiple choice questions, if I'm not mistaken. And then they have 15 more multiple choice questions, but that's where you use a calculator. It use Desmos now. Now Desmos is allowed because it's all on the computer. And with those 15 questions, I think you get 45 minutes. You get 3 minutes per question. But there's a kind of a skill set, and I think actually, to be honest, I think the calc is actually better to use than Desmos. That's a skill set I won't teach you guys. You'll learn that next year in AP Calculus. Then you take a break, and then after the break, you do six free response questions. The first two are calculator allowed, so you hold on your calculator. Then you do four non-calculator questions free response after that. And you get 15 minutes per, so it's about an hour and a half. So overall, it's about like a almost a 4 hour test. For those with, I've had some students with double time. They're there for 8 hours. It's a pretty long test. Anyhow, now let's get to the fun stuff. Okay, that was all just like very, very basic. Now we're gonna start actually talking real calculus here, right? Um, so y equals x squared. Let's consider that, right? And let's look at these points here. So yeah, 7 comma 49, 5 comma 25, 3 comma 9. What you're noticing is that point P is static, right? Point P is stuck at 1 comma 1. Point Q is moving. And point Q is moving closer to what? A 1. X coordinate point Q is approaching. Let me hold on. Let me fix this. A point Q is approaching the X coordinate of point P. That's what's happening. The X coordinate of point Q is approaching the X coordinate of point P. So as they get closer and closer and closer, that's what's happening. So what do you notice is happening to Y? It's getting smaller, right? But ultimately, it's getting closer to a particular Y value, right? But we're going to really more look at the slope, though. That's what we're more interested in. So let's find the slope between point Q and point P. So for example, if I find this slope, I would just do 49 minus 1, which would be 48 over 6, which would be 8. So all I just found the slope of point P with Q1, right? Point P with Q1. So the slope of P Q1 is 8. And the hope is that the slopes will eventually converge to a certain value. So what we're hoping for, let's compute the slope of the secant line for various values of Q as Q approaches P along the curve. That's exactly what we're talking about. That's what I talked about up here. As Q approaches P, the x coordinate point Q is approaching the x coordinate point P. So why don't you guys do this? If you guys have calculators, or you can use your devices, not your cell phones, but your iPad or whatever, calculate the slopes for all the other ones. This is just a good little exercise. It should take a few minutes. I do have this fully worked out. I'm going to show you the worked out solution. And then we're going to have a discussion about what's happening with the slopes. So find the slope between 1 comma 1 and 5 comma 25, 1 comma 1 and 3 comma 9. Then if you do plug a 1.5, do you guys know what's the input? Sorry, the output? 1.5 squared, 15 squared. That's right, I'll tell you guys right now. I'll be your calculator for you. So 2.25, 1.69. So you're gonna be finding the slope. You're gonna be finding six more slopes. And let's see what happens. I know it's kind of a mundane process, but I think it's important for us to do. And let me freeze. Let me pull up the solution key. So yeah, again, you guys are doing very simple calculations. What do you get for the second slope between 1, 1, and 5, 25? 6. Keep going. All right. Keep going. You're gonna notice a convergence. Meaning you're gonna be noticing that ultimately the slopes settle on a particular value. Also, as Q is approaching P, the slope becomes less of a secant line and more like what? That's the key idea. We're trying to create a tangent line. We're trying to find the slope of the tangent line, but the problem is that you're still passing 2 points, right? We're not just grazing 1, 1. And this will be the aha ta-da moment in just maybe a few minutes. We'll get there. This is the part I really like. I get very excited about. Okay. Um, I'll show the answers. Hopefully you're getting that. Slope is 4. Then you should get 2.5, 2.3, 2.1, 2.01. I mean, you can get even closer to 1. Like you do 1.00001, right? So we get awfully close. Now, what do you think the slope is settling on?
Two.
2. Now, how do you think limits are going to play a role here?
What slope is it?
What is what, sorry?
Slope is it?
Correct, but I'm going to take the limit as what approaches what. P approaches P, but let's get even more granular, right? We're looking at the difference. What's happening to the denominator every time? Getting tinier, right? So I want the x coordinates of point Q to get closer to point P. Or I want to change in x to get closer to what?
0.
You guys see how this is a limit? I want to take the limit as delta x approaches what? 0. And I'm taking the limit of what? Of the slope here. I'm taking the limit of the slope. That right there is the derivative. We're going to talk about that in just a moment. But right now, what we've done. So yes, does it appear to be approaching a certain number? Of course, approaching 2. Notice that the secant line as point Q gets closer to point P begins to look like the tangent line at point P. Not exactly, but it's looking like it, right? So given 2 points, P and Q on a curve, if the slope is calculated each time point Q moves closer and closer to P, and the slopes are approaching a limiting value, it's like a limit if it exists, this limiting value, if it exists, is called the slope of the curve. And um, um, shoot, I should know this term. Um, well, actually, you know what? I thought it was some other fancy term, so I should know this. The derivative to the curve of P. It's going to be the derivative. So therefore, find the slope of a curve at certain points, like find the slope of the tangent line. And limiting value or slope of the curve of P is no longer called the average rate of change, but rather is now called the instantaneous rate of change. So it's the same thing. The derivative is the same thing as the slope of the tangent line. We call it instantaneous rate of change. So for example, driving from here to Los Angeles, right? You know, your average speed was 80 miles per hour. But let's say you're passing like the middle of nowhere. I can't remember this. It's a long time since I've done that drive, but you know, you say you want to stop to go get food at In-N-Out, or there's a Chick-fil-A, or get gas, or use the bathroom, whatever, right? What's your speed at that moment, right? Or what's the speed right when you see the cops? It's like that's instantaneous rate of change at a particular moment. What is your speed? What is the speedometer saying in the car, right? That's what we're interested in finding. So we call that a derivative or the slope of the tangent line to the curve. So yeah, so a slope of a tangent line of a curve at a point expressed in words, we'll need to define this mathematically. So when we talk about it looks like it's going to be a limit, right? So slope of the secant line, what's happening here again? It's f of b minus f of a. Actually, in this case, because using x and a, my apologies. F of x minus f of a over x minus a. That's that line. But the tangent line, x is getting closer and closer to what? What do you want x? If you want to get a tangent line, you want x to get close. This x right here is my second x coordinate. You want to get closer to what? Well, you want x minus a to get closer to 0, or x to get closer to a. Yes, exactly. So the way you're going to write it is going to be like this. You're going to write as the limit as x approaches a of f of x minus f of a over x minus a. Is you're going to write as the limiting case. Sometimes we use delta h as well. Sorry, we use h or delta x. So h is delta x, or it's like b minus a. Actually, I'll just call delta x. So x itself is a plus delta h. Sorry, a plus h. My apologies. So x itself would be a plus h.
Wait, so whenever we find derivative, you always need to like find figure out all of the or
Yes and no. Initially, by the way, I'll call h x minus a right now because it is x minus a. Initially, yes. Later on, no. Because to do the limit of all these expressions, you're going to drive yourself crazy. We're going to do that actually tomorrow. But there are shortcuts, and I'm sure you guys could look online, guys. You know the shortcut rules. I'm not going to say them right now, but ultimately, that's not very practical. So you will learn these like more efficient ways down the road. Sometimes I will ask you to use the form definition of derivative, yes. And the reason why is because you have to understand where it comes from in order to make sense of all the other stuff you do down the road. Also, you are expected to know that too, like just like there's ways they can, the College Board can twist the form of definition of derivative, and they'll like assess, and you have to be able to recognize it, if that makes sense. So, but that's what's happening. You want to take limit as x approaches a of this expression here of the slope between a comma f of a and x comma f of x. And this is when x is approaching a. And you could think of x minus a as h or delta x, or x is a plus h. X is a plus h. So you want h to be going towards 0, essentially. So in other words, here's what we want. You want to take the limit which is going to equal now it's going to look a little confusing at first, so bear with me. I'll explain in a minute what's happening here. That's what that represents. So first off, we already saw this, right? We know we want to limit the case. Replacing x with a plus h. If a plus h is approaching a, then what is h approaching? 0. There we go. And replace x with a plus h, and x with a plus h. What happens to the bottom? What happens to the ace? It cancels. So this is a very standard formula. This is the limit definition of the derivative. We'll talk more about this tomorrow. Um, or we think of it as the slope of the tangent line at x equals a for f of x, or the derivative of f of x at x equals a. So for the secant line to become a tangent line, h must be approaching 0. This means you take the limit as h approaches 0. Thus, the slope of the tangent line, I already wrote for you guys, is right there. I'm not going to write it again. It's the same thing. Okay, any questions? We good? Okay, so let's keep moving here. Yeah, the notes are a little off of the formatting. I apologize about that. I didn't make these notes. So let's give it a try. Let's try them right now. And I think just looking at how far I want to get, maybe we'll get to example 5. That might be a good place. Yeah. So we'll keep going. Okay, so slope of the curve. Okay, let's just go to the example. I don't know what's going on here. You guys get the idea. So let's look at the example. Okay, given the parabola, use the definition of the slope of a tangent line to analytically find. So we expect the answer. We expect the slope to equal what again? At 1, 1 for x squared. What do we just do in that table? What slope do we get? 2. So here's how you can do it. You can do the limit as h approaches 0 of f of 1 plus h minus f of 1 over h. Because what's happening again, here's what's happening. You got a problem, right? You got the point 1, 1. Then another point's really close to it, right? I'll call this 1 plus h, comma, f of 1 plus h. I'll put a bracket here so it stands out a little better. Right, that's what we're doing, right? I'm trying to find the slope between the pink and the green dot, right? I'm trying to find the slope. But here's the thing. Right now, if I draw the line between these 2 points, that's a secant line, not a tangent line. What has to happen to make this a tangent line again? H has to be getting closer and closer to what? Well, 1 plus h is getting closer to 1, or h is getting closer to h is getting closer to 0, right? Yeah. No, you got it. Yeah, h is getting closer to 0, right? So that's what we want. We want this to get closer to 0, so that's the way we get a true tangent line, right? Now this is where the real fun begins. And yeah, you guys won't like this. You guys actually hate me when I show shortcuts. Like, what the heck, mystery? Like, seriously, you will probably say that. Maybe not. Maybe you guys are kinder. I'd not give you guys benefit of the doubt. Anyhow, here's what you're gonna do. F1 plus h. You're gonna do 1 plus h squared minus 1 squared over h. Right? Because isn't f of 1 just squaring 1, right? And 1 plus h you have squared, right? What do you think is gonna happen? What are you supposed to do? Expand it. Yeah, FOIL, 100%. Yep. And you have to keep writing limit notation. Can't get lazy here. Now, fortunately, some things do cancel out nicely. What cancels out? The ones. They should. If they don't, you're making a mistake. At the same time, I can factor on h, right? You guys see I factor out the h from 2h plus h squared? Now, what goes away at this point? So now you got this, right? Now, if you plug in 0, what do you get? You get 2. Congratulations, you did your first derivative. Or maybe you've done it before somewhere else. I don't know. That's a derivative. That's what you just did. You now found analytically the slope of the tangent line of x equals 1. Now you look at this like, geez, like I have to do this like every time. No, you don't have to. Trust me. You don't have to just like for now, we have to do it this way, but in a couple weeks, maybe before you leave for ski week, I'll show you the shortcuts. And you'll appreciate like, okay, yeah. Because there's a shortcut for this. By the way, does anyone know what the derivative of x squared is? And
2x.
it's 2x. There's a shortcut that we use for that. I'm not going to talk to the shortcut is. You can look it up. There's a shortcut you can use for any monomial term, and then you just plug in the x value and get the derivative. It's super easy. Like you look, it's like, why did I do it this way this whole time? But we have to do it this way for now. By the way, what was that?
Like the
Yeah, so what we're doing is we're simplifying this expression so that we can get the numerical value of the derivative at x equals 1, or to get the slope of the tangent line at x equals 1. And they did ask for the equation of tangent line. We do need to do that. By the way, when you guys do equation lines, just use point slope form. I do not care for slope intercept. You want to simplify? Go ahead. I don't care. Just leave it like this. Actually, the College Board prefers you do it this way. So just get in the habit of doing that. Y minus 1 equals 2 parentheses x minus 1. Just do that. Because remember, what's the point on the line? 1, right? And what's the slope 2? So if I were to graph y equals x squared and graph the green equation, you would see the tangent line. If you got one of the Desmos for your TI-4 calculator, you would see it just do this, right? There you go. There's a tangent line. Again, if you want to simplify it, go for it. It'd be y equals 2x minus 1, I think, but I don't care. Okay. You guys ready to try one? Try another one? Because try another one. Let's look at example 4, right? Oh boy. Yeah, so it's kind of crazy. Yeah, now you guys will get upset at me. Um, we're doing limit as h approaches 0. Now we're trying to find the slope at what point? At 2, right? And by the way, if you're to graph this, I think it looks, you can factor out x. I think it crosses at 0 at root 2 and negative root 2. And I think there's a point like right here. Kind of missed it. I think that's what we're looking at. So what you're doing is this. You're doing f of 2 plus h minus f of 2 over h. Right? What do you think we're doing here? How do I start this analytical process? I'm plugging 2 plus h into what? So I got to raise 2 plus h to what power? Yeah, the third power, I know. There is to the third power. Ugh, it's gonna be a little nasty. We'll deal with it. So limit as h approaches 0. Make a big bar there. So 2 plus h cubed minus 2 times 2 plus h minus bracket 2 cubed minus 2 times 2 all over h. So let me get a highlighter here. So my tools are kind of cool like that. So you got this right here, and then you got this right here. Just so you're not confused, you see how the pink highlighting goes with this, the yellow highlighting goes with this. I use brackets. I want you guys to be very proper to write this so I can easily see what you're doing. It's really easy to kind of be all over the map here. You want to be very organized in your approach. Now the yellow is easy. What's gonna be in the yellow? That's easy. What's that? 4. Yeah, I agree. You get 4. The bottom is still H. Ugh, I need a little more space here. Actually, I'll do it over here. All right, well, okay. Usually off to the side, I'll do this. Did Mr. Van teach you guys binomial theorem? Like where you expand like a binomial to some power?
Um,
Did he teach you combinations? NCR?
Yeah.
Okay. It's okay. Do you guys remember Pascal's triangle? Okay. Well, you know what? Let's just FOIL it. It's fine. Uh, I can get really fancy here, but I'll just FOIL it for you guys. Do you guys see I multiply 2 plus h with itself first to get 4 plus 4h plus h squared?
Mhm.
About to multiply it again. And just trust me, I think this is it. H squared, sorry, h cubed plus 6h squared plus 12h plus 8. I think I did it right. Yeah. Cool. So that's what's happening. You have h cubed plus 6h squared plus 12h plus 8 minus, I need a little more space here. Minus what? Let me look at this part here. Minus 4 minus 2h. And of course, still the minus 4 from earlier. Yeah, when you're doing the homework, please don't curse at me because you're gonna have to do this a lot. What happens to the eights? The 8 and -4 those cancel, right? They should. Otherwise, you're gonna run into a problem. And if you clean it up, you should get h cubed plus 6h squared plus 10h all over h. I think I did it right. Yeah. Yeah. Yeah, I did it right. Okay. And then what can you do from the top? Pull out h. And I will post the solutions for this when I get a chance to populate Schoology later today. So you can see all the models. And this is someone else's handwriting, not mine, so it'll be very legible. So those cancel. Then you could plug in 0, which I'm going to need some space here, so I'll get rid of all this stuff here. But notice that when I cubed 2 plus h, I did off to the side to kind of handle that. And so now I just do 0 squared plus 6 times 0 plus 10. And what's your final answer? 10. There you go. It's a pretty steep slope as it should be. Yeah. Now, there's a shortcut for doing this. So Luke, since you got the last shortcut, do you know the shortcut? For x cubed minus 2x.
isn't it like when you put power in table?
Right. You move the power to the front, subtract by 1. So the derivative of x cubed is 3x squared. The derivative of -2x, because if you see an x, you assume the power is 1. Move to the front, drop it by 1. The derivative that's actually 3x squared minus 2. But we're not there at shortcut rules yet. I haven't taught you guys shortcut rules. For now, we're just doing this. So you get 10. Okay. Let's stop there for today. This would be a good place to pick things up. So exam 5, I think would be a great place to pick up tomorrow. And I should definitely be able to finish off these notes and kind of start talking about derivatives for a little bit. Homework will be, let me take a look at the homework what I want to assign. Oh, sorry, there's a question?
Would you point to and
Oh, yeah, exactly. Sorry, did I ask for that? Oh, yeah, sorry. Let's do that really quick. The normal line, actually. The normal line is actually a perpendicular line. So again, our graph was like this, right? Our tangent line was like this. So a normal line, for those who are taking physics, what does normal mean?
Like perpendicular.
Yeah, like normal force, right? When you're looking at ramps, like when you look at friction and things like that, for those who are taking physics. So you want a perpendicular line that's perpendicular to the tangent line. There's actually a very close tie between calculus and physics. Um, some people say like, so calculus was invented by two people, Sir Isaac Newton and Leibniz. But with Newton, he basically needed a mathematical technique to make his physics applications more manageable, or his physics calculations more manageable. So some people say he invented calculus to make that happen. But anyhow, you want perpendicular to the tangent line. So if your slope of the tangent line is 10, what's the slope of the normal line then? Negative 1/10, right? So you're going to do y minus, if you plug 2 in, you should get 4, because that's 2 comma 4, right? So y minus 4, negative 1/10, x minus 2. That's the equation of the normal line. Yeah, I think it's a good place to end for today. So, homework, look at the problem sets. What seems reasonable? Definitely 1 seems reasonable. 2 seems reasonable. 3 seems reasonable. 4 seems reasonable. Um, kind of hold off on 5 with square roots because I want to do more with you guys, as well as 6 and 7. So we'll just be 1 through 4. Homework will be 1 through 4 in the packet of Hannah Day. I'll put this in school, G. So we 1 through 4. As you can probably imagine with number 5, you'll probably have to do a conjugate to to do that analysis. And 6 will be kind of a funny one, but we'll talk about rational expressions tomorrow. Yeah, I think that's a good place to leave things for today. Yeah. Okay. We'll stop there.